Hi, it's Terry Denner of the MathWorks. So anyways, let's continue with this. And so let me just kind of validate a little bit my suspicions that there's a problem with the controls. And so we'll go into the motor controls that are on the plant side. We got that PID right there. And so I put a scope on the angular velocity, and that's the job really of the feed forward and feedback through the PID to really hit the command, and it looks beautiful. And that, what's happening kind of on the ascension, that's all taking place up to here. And these, additional thrust adjustments, they're really pretty small compared to even the thrust variations are taking place to halt the ascension and to kind of do all the things we're doing on that. So anyways, but that's all taking place here. So I'm going to just kind of zoom on this part of the curve, and I'll hit this. And here we'll see that at the kind of scale at which thrust differentiation is going to occur, or what's called the speed differentiation of the propellers, that it is a little bit loose still. All right, and so we're seeing all that oscillation right there. Right. And so anyways, kind of we're going to go into the PID, and we will retune. So right now, proportional is around 10, integral is around 200, and derivatives, pretty small compared. So the PID tuner is going to even, again, according to its own algorithm, which is really kind of based on an optimization, I'd say that probably broadly addresses kind of recognize, kind of good performance values for rise time, settling time, and so forth. Kind of came up with this configuration, and I think that's where we were pretty much operating before. And so I'm going to just make it a little bit faster. And so I'll put it here. And so this is what it would, its response to a step function would be now. Okay. So anyways, let's go ahead and close that. Let's update the controller. Shut that down. Those new values are now in there. And let's replace the controls for the other three motors too. So we'll just copy and paste. And of course, the bottom two spin in an opposite, the bottom two being the ones on the y-axis, spin in an opposite direction. So let's account for that. And let's hit run again. Okay, so it runs pretty quick. I'm going to bring us to 117 seconds. We'll look at that view. And it's looking pretty good. Now I check my, I still got a bit of a problem though. Okay, and so I want to dive into this a little bit more now, right? And so we're still kind of getting kind of messed up angles as things accumulate. So let's go back here and let's see, did we fix that? Right, and so, and I'll just kind of zoom in on this portion of the curve. I'll hit that. And I would say we're looking pretty good on the control. Now we might be even more aggressive, but what I'm now of the opinion is, let's check the simulation, right? And so I'm going to go to model settings. Right, we got all kinds of stuff in model settings for Simulink, but I'll go to the solver page, and you'll see the numerical integration. Well, that's where all these choices are made. You're doing like third, fourth, fifth, I think eighth orders in there, all kinds of approaches. And you get both variable step and fixed step. Anyways, but what I want to kind of get at is what governs the variable time step choices is these accuracy settings. And so I'm going to make them a little bit tighter. And we'll maybe run it from here this time too. And what we should see is just this 5-degree displacement, although it might be in radians. I should have multiplied that by 2 pi, I guess. But you can see it's slight. Am I trying to do the math in my head? Well, what I'm seeing is a nice clean signal. Perhaps in the next video, I'll kind of fix that. Well, all right, we're there. So let's just kind of do a little local fix. And so I'll put in a gain. And we'll put it on that signal, which I believe is the blue one. And so we'll multiply by 180 divided by pi. Right, and that'll convert radians back to degrees. What did I do wrong? No. Don't need to put the multiplier in there. Okay. And we'll run that one more time. Now, isn't that beautiful? So right on 5 degrees. So anyways, I'm feeling real good about things again. So there was a bit of an issue with the controls, and so we did tune it up, and that worked pretty well. But we also always got to kind of check and make sure that, is the simulation itself legitimate? And is it, one of those ways of checking is the numerical integration itself occurring kind of stably and accurately? So anyways, to wrap up this video, I want to do a couple of things. We do have this opportunity. We've started rotating over 5 degrees, and we talked about it required a thrust adjustment. So let's see. Yeah, this is a good one. So we'll see how essentially the vertical position drops off. And that's really because we're losing a vertical component of thrust, and it's no longer enough to kind of compensate for gravity. And so we kind of showed the fix in the previous, I think, 2 videos ago. And so I'm going to just kind of throw it in again. And so it's really this idea that, oh, I didn't even put it in. All right, so let's go in here. So torque IYY, let's get the selector on angle from here. Angle will be the first component of PVA. And I will just call that angle. All right, and so that angle will fill right here. And that this no longer is the thrust, but the adjusted thrust is by taking that and operating on it with that angle. And so with that, then we got to refill all these. And we're not doing anything with the X rotation because it's pretty much the same thing as the Y rotation. Of course, Y rotations occur through X thrusters, where X rotations would occur through Y thrusters. But I think we got it set up properly with that now. And well, let's find out. Let's run this one more time. Isn't that cool? All right, and I think I'll do one last piece on this, and I'll take a little bit more sophisticated trajectory, which will be a little bit more fun to look at. All right, and so let's paste that in like this. Okay, and we'll compare this angle with what's coming off that. And do that same conversion back to degrees, and we'll observe that component, and we will run this one a little bit longer. Let's run it 230 seconds. There's also going to be a translation in X that we're already observing, and I just want to measure it this time. And so, I'll hit run. I'll take a look at this scope and see how we're doing. Looks like we're doing pretty well. So we're hitting those rotation angles quite well. And I'll show the X translation right here. And we'll see that we do travel about 500 meters in the horizontal direction. So anyways, as I said, quadcopters are kind of fun. And the mechanics is so interesting to me. So anyways, we'll move into a few more things. And I'll just kind of mention that I might show a few things on the what I call the Z rotation, the rotation about that vertical axis. It's definitely tougher. Not sure I have the definitive solution. Not sure anybody really does. It's definitely a harder problem. And it has a lot to do with the fact that the same thing that you're using to generate thrust is what you're going to use to rotate it. And so maintaining what you need out of thrust and at the same time kind of getting those torques generated by differentiation. It's a little bit harder with Z. I think the next video I'll still kind of address it and we'll kind of see where we end up with it. So anyways, thank you.